So in this question here, we're going to find the inverse Laplace of 6 over s squared minus 4 and add it to the inverse Laplace of 3s over s squared minus 4 as well. Now, in previous videos, I've done the inverse Laplace of similar looking questions, but with a positive sign. And when we do that, we get sine and cosine accordingly. Now here we've got minus sign, so just to put sine and cosine in there is not going to work. So let's see how we can solve this. Well, first of all, s squared minus 4, I know I can factor that out into s minus 2, s plus 2. So let's do that. So this first one, 6 over s squared minus 4, I can rewrite that as 6 over s minus 2, s plus 2. Now from there, I'm looking at partial fraction decomposition in my inverse Laplace techniques that I've shown you before. So here, let's break that down into its components. So s minus 2, s plus 2, my building blocks will be as this. And then what we can do now, we can use the Heaviside cover-up method and get each one to disappear, and then we can find the value of that one. So for A, I want s equals 2. So s equals 2. That will lead me to find my A. So A will now be 6. 2 minus 2, that disappears. Then I've got 2 plus 2, which is 4. So A is 6 over 4. So that's 3 over 2. So that's great. That's that one sorted out. Now B. So for B, for the Heaviside cover-up, I want S to be minus 2. And that's valid because we've used different values for our cover-up method. So that's good. So now for B, plug in minus 2 into here. So I still have 6 in the numerator. Minus 2 is minus 4. And then that one will be disappeared. So then B equals minus 3 over 2. So that takes care of my partial fractions. So now I'm going to have this one here. So the inverse Laplace of 6 over s squared minus 4. I can rewrite that as the inverse Laplace of 3 over 2 over s minus 2. So I can write that 3 over 2 times s minus 2. And this one I can write that as a minus. So I'll just put a minus sign in there instead of positive. 3 over 2s plus 2. Okay, now just put a bracket in there just to make sure my algebra is good. Now here I've got 2 over s minus 2. 3 over 2 s minus 2, 3 over 2 s plus 2. Now here, my general formula I can use is my inverse Laplace of c over s minus a. That is c e to the a t. So these ones here, taking out my constants, I can write the first one. So the inverse Laplace of 6 over s squared minus 4. Now here 3 over 2, so I can have a constant. So 3 over 2. And then I've got s minus 2. So that would then give me, in this format, e to the 2t. So e to the 2t. And then I'm going to have to subtract it from 3 over 2. And this time I will have e to the minus 2t. So that would take care of my first one. So let's take this off the board and we'll have a look at the second one and see what result we get for that one. Okay, let's concentrate on this one now. So now I've got 3s over s squared minus 4. So as I did before, we can factor out the denominator. So 3s over s minus 2s plus 2. And then set that up into partial fractions with my building blocks. So I'll have a over s minus 2 plus b over s plus 2. Okay, so now Heaviside cover-up method is going to work again. So for my a, again I want s equals 2. So therefore my a will equal, so I've got 6 again in my numerator. If s equals 2, this one's gone, and this one just becomes a 4. So I've got 6 over 4, so that's 3 over 2. So A is 3 over 2. And now for my B, I want my S to be minus 2, very similar to the last example. S equals minus 2. So therefore my B equals, well, minus 2 into this, I'm going to get minus 6. Minus 2 is minus 4. So this time B is also going to be positive 3 over 2. Okay, so now plugging that into my Laplace transform of this. So now my inverse Laplace, open the bracket, I've got 3 over 2 s minus 2. So 3, 2, s minus 2. This time I've got a positive 3 over 2 s plus 2. Okay, now this time I can use my general formula again. It's of the same kind of format. So now let's put in my result onto here. Let's see where we go. So now the inverse Laplace of 3s over s squared minus 4, that would lead me to, well, I've got 3 over 2 again, and s minus 2, well, with a minus 2, e to the 2t. So that takes care of that. And then this one, very similar, 3 over 2, e to the minus 2t. So plus 3 over 2, e to the minus 2t. Okay, right, now where does this take me? So what I want to do now is take this off the board, and then we'll have a look at these two results in terms of our original question. Okay, so now I've got all my results for my inverse Laplace transform so far, using these two results here. So now what I'm going to do is I'm going to break these apart into the two separate results that we found earlier. So that's that one, and that is that one. And now what I can do is, maybe I'll factor the 3 over 2 out of each of these exponentials. So now I've got 3 over 2 e to the 2t minus e to the minus 2t. And the same with this side. It's 3 over 2 e to the 2t plus e to the minus 2t. Okay, so now that I've done that, I can see here now I'm almost at my exponential identity for my sinh and my cosh. Now what I know is that sinh of lambda t, for example, that in exponential will be 1/2 and e to the lambda t. So lambda t is that sinh input, and then I subtract e to the negative lambda t. So that's the exponential identity for sinh. Now cosh is very similar. Now cosh, for example, of lambda t, that is very similar to this with 1/2, open bracket, and then I've got e to the lambda t plus e to the negative lambda t. Notice just the minus sign and plus signs. Now here I've got very similar things going on. So here I've got 3 over 2, and here I've got 3 over 2. So what I could do, change these to 1s and multiply by 3. That will be legitimate, I could do that. So then using my exponential identity here, this result now becomes 3 sinh of 2t plus 3 cosh of 2t. So therefore we've shown here, when we've got a minus sign here, for example 6 over s squared minus 4, that will give me sinh of 3 2t. So we divide this by the square root of this one. So for example we can say here lambda over s squared minus lambda squared, that will give me always sinh of lambda t. And then similarly for this one, and then for cosh of lambda t, we've got s over s squared minus lambda squared, that will equal cosh of lambda t. Okay, so this is our functions here for our sinh and our cosh. And the Laplace inverse transform of these functions, that is the answer here. Okay.